Okay, then let's start. The next speaker is Dr. Oscar Ocampo from University Federal de Bahia. His talk title is on the connection between crystallographic groups and generalized braid groups. Please.
Okay, thank you, Professor Kamara. I would like to thank the organizers for the opportunity to share my work here in this great conference. It was supposed to be in person, okay, but in other moment maybe we met together in person and share these works. Okay, so let me speak about this connection between crystallographic groups and generalized braid groups. It means, for generalized, it means some generalizations of the classical Artin braid groups. First of all, let me say some words about crystallographic groups. They are, from the geometric point of view, they are discrete and co-compact subgroups of the isometric group of the Euclidean space. Initially, they were motivated for these wallpaper groups, the two-dimensional ones, and in three-dimensional case, they are really motivated for crystals in the natural sense. Okay. So after that, some people generalize the notion of crystallographic group, and we use here this. Let me see here. Okay, here we shall use this algebraic characterization of crystallographic groups that, for our purpose, is very interesting and it's very useful to see crystallographic groups in this way. So how it works? From the global point of view, when you have a short exact sequence in which you have a free abelian group here, a finite group here, so you may consider the conjugacy action projected to this quotient, okay? And you ask if this action is injective or faithful, okay? If it works, so you say that the middle group is a crystallographic group. Some definitions, the finite group is called the holonomic group of the crystallographic group. And the integral representation here, recall that you have here the finite group in the domain. So this representation is called the holonomic representation. These words come from Riemannian geometry. In fact, when you have crystallographic groups that are torsion-free, you say that they are called Bieberbach groups. So Bieberbach groups, let me see here. Okay. So Bieberbach groups are these torsion-free crystallographic groups. They are very interesting because from some Bieberbach theorems, you have a correspondence between the flat Riemannian manifolds. This means zero constant curvature, and the crystallographic groups that are torsion-free. So you have these two classes. There is a bijection via the fundamental group when you take up to isomorphism in the crystallographic, for the crystallographic groups, torsion-free ones. For the flat Riemannian manifolds, you need to take up to diffeomorphism. So, because this correspondence from Riemannian geometry and group theory is very interesting to study Bieberbach groups and try to understand a lot of information, because the information, the algebraic information that you may obtain from the torsion-free crystallographic group, it means the Bieberbach group, you may conclude some information about the flat Riemannian manifold that is related to this group. So it is an interesting family to consider and to study some properties. Okay, Well, we shall use this algebraic characterization of crystallographic groups here. But before, let me say the motivation, the first steps in this connection. So the first connection, in fact, was given for the classical case for Artin braid groups in a joint work with Dacifer Gonçalves and John Waschke. In few words, it works in the following way. So you have the classical short exact sequence of braids. Sigma is the canonical projection of a braid into the symmetric group, and the kernel is the classical pure braid group, the classical one. So you may take some kind of quotient of this sequence, taking the commutator subgroup of the pure braid group. So in this part, you will have the abelianization of the pure braid group. And in the middle group, you have the quotient of the total braid group mod the commutator subgroup of the pure braid group. And you may consider the action, okay, the conjugacy action when you see it from this quotient. So try to understand how it looks like the conjugacy action. And the conjugacy, the action by conjugacy is just take the behavior in the index of the pure braid element. So when you take this conjugation, just try to apply it for the same element when you take the action in the indices of this Artin generator. Okay, so it is completely clear that the action will be injective from this definition. And we show that the middle group here, in this short exact sequence, is here means, let me see, the pointer. So in this short exact sequence, the middle group is a crystallographic group. This is the holonomic group, and we obtain some holonomic representation. Okay, so this was the first connection between some braid-like group, in fact the classical one, and crystallographic groups. So when we have this kind of group, immediately we try to obtain some properties of it, in particular some properties of its structure. So we prove some of the properties, in particular how is this group inside it. So we study finite order elements. In particular, we prove that the torsion, the finite order elements in this quotient group is equal to the odd torsion of the symmetric group. And recall that the classical Artin braid group, is torsion free, but this quotient, in fact, is now has finite order elements. And since it has no elements of order 2, we may create easily some kind of Biberback groups. Okay, so torsion-free crystallographic groups. So a natural question is the following. There are a lot of generalizations of the Artin braid group. So we have virtual braid groups, surface braid groups, another kind of braid-like groups. And so this is very natural to ask which other braid-like groups have similar quotients that are crystallographic groups. So in order to do this, I will explain a little bit about which works and which results we have in the literature at this moment. So for a moment, take this generalized braid group, GBN, and it will be denote one of the following groups: the complex reflection groups, or surface braid groups, or virtual braid groups, virtual twin groups, also singular braid groups, or virtual singular braid groups. And when you take, let me see here, what means for me a canonical So you have a lot of strands, and you have some I place one here, and you take here some kind of crossing, maybe classical, virtual, singular, flat, etc. Okay, even in the case of twin, some kind of twin crossing, and so you may associate to this crossing the permutation I plus one for all of them. You may try to do that. Okay, so in this way we define a natural map from the total group into the symmetric group that send the canonical generators to the respective proposition. Okay, and so consider the kernel of this homomorphism, and the kernel will be the pure braid respective object in the kind of generalization that we are considering. And so obviously we may construct this kind of short exact sequence. It is completely clear. So doing that, we have the following result. So when you have this kind of generalizations, okay, also the other one, this is the total group, this is the pure counterpart, and you may consider this short exact sequence, okay. Here, for me, gamma 2 of Pn or GPn means the commutator subgroup. It's the second step of the lower central series, so it is the commutator subgroup of the group, okay. So it's just the commutator sub. Okay. So this kind of result means that the middle group is a crystallographic group. Okay. This is a crystallographic group, and we have here the holonomy group, and this is in most cases this is a free abelian group. So if you have a free abelian group, you have a rank, and this is the dimension of the crystallographic group. Okay, so for the group that I cited before, for example, for complex reflection groups, it was proved from Ivan Marin, joined with Daciberg, Gonçalves, John Warski, and Carolina Pereiro. We proved it for closed orientable surfaces different from the sphere. And the result for non-orientable surfaces is that the middle group is not a crystallographic group for the non-orientable cases, because this group is not a free abelian group. It has torsion elements. So this result holds when you have closed surfaces, orientable, different from the sphere. In a PhD thesis, was proved for finite nature surfaces. Then, more recently, Bardakov et al. Stated that this quotient is a crystallographic group, and in fact, it is the symmetric product of the 2 points. And also, in a joint work with my student Paulo Santos, we proved it also that the quotient is crystallographic group, but these two works are different in a sense. They study other problems different from the ones that we study here. So there are not exactly the first steps are more or less have they coincide, yeah, establishing that the middle group is a crystallographic group, but then we study different aspects. Okay, and also for my student Paulo Santos Jr., he proved that for singular braid groups and virtual singular braid groups, also the middle group is a crystallographic group. So it's interesting in these works. It's interesting to establish that this group is a crystallographic group and then obtain some properties of this kind of group. let me say a few words about the virtual braid information that we have. So now let me talk about virtual braid groups with a little bit more of details maybe. So we have the virtual braid group, and it has a decomposition as the virtual pure braid group and the symmetric group. So it is a semi-direct product. We have a natural section, and the group of virtual pure braids admits the following presentation. And it is very easy from the presentation that when we abelianize this presentation with this group, we obtain a free abelian group, okay? And so we have this kind of a split Schur exact sequence, and we project to this kind of quotients, okay? Here we have a free abelian group that has rank n times n minus 1. And it is not difficult from a lemma in the article of Barbacov that the action, in fact, is very similar to the action in the classical case. It's just consider the action of the element in the indices of the in this case the pure virtual braid element. Okay, and so following. It's completely clear that the action is injective, and so following the characterization of crystallographic groups, it's completely clear that we have this social exact sequence for virtual braid groups, and the middle group is a crystallographic group. Okay, so it is just to apply this characterization, and it is really very clear. So, as I said before, it's interesting to obtain some kind of properties of these quotients, not just establish that they are a crystallographic group, but try to obtain some information. So let me say some few words about this. Bartholdi et al., they show that we have an injection of the pure braid group inside the virtual pure braid group. So the important part is this kind of diagram. So we have the respective quotients. This is the classical case here. Okay. And in the other row, we have the virtual braid part. And so from the result of Bartholdi, we have an injection for the pure virtual, for the pure part, so the abelianizations. Okay. We have an injection, and so applying the 5 lemma, we conclude that we have an embedding of the classical case into the virtual braid case. Okay, so in this point, we may conclude the following information. So since we have this embedding, all the information about elements inside the classical case we have in this generalization of the virtual braid group. So it means in this here, so in this quotient, for example, we have a lot of finite order elements that comes from the classical case. We have a lot of Biberba groups that comes from the classical case. Yeah. So for finite order elements, we have a characterization in this paper of 2017. So we characterize all finite ordered elements inside the quotient of the classical Artin braid group. Okay. And in this other paper, was possible to realize families of Biberba groups with holonomy, a finite group which is abelian. Okay, so we have a lot of Biberba groups, a lot of finite ordered elements inside the quotient of the virtual braid group mod the commutator subgroup of the virtual pure braid group. But also in our work with Paulo, oh, sorry, okay. So in our work with Paulo, we also try to characterize finite ordered elements here, also conjugacy classes of these finite ordered elements, also realize a lot of Biberback groups. These are different elements and different Biberback groups. There are, in fact, there are different elements and different Biberback groups from the ones that comes for the classical case. Okay, so it was proof in this joint work with Paulo. The idea is try to consider some equations in the integers that comes from the different action applying many times. Well, now in order to talk about other kind of generalized braid groups, there are this kind of quotients of the virtual braid groups. So let me talk about some of them. So we have, come on, here we are. So we have welded braids and restricted virtual braids. We have flat virtual elements, flat welded braids. So this part is for virtual braid groups. And also we have here virtual twins. And they are connected. They are connected from these two bigger groups. When we have some quotients, these maps are epimorphism. That means we have some quotient. And so they are connected from this flat virtual braid group. But also we may define, this was doing by Bartakov et al. We may define welded twin groups, and also we define with Paulo this Gauss virtual twin group. It is possible to try to explore this connection with crystallographic groups with this kind of quotients of elements. But okay, but the point is, we may try to do that, but when we have here colors, and trying to explain. When you take the respective quotient, not the commutator subgroup, and also here, we prove that these quotients, the groups are not isomorphic, but the quotient, when we take the commutator subgroup of the respective pure part, sorry, this is also pure part, unrestricted, pure part also. Okay. So when we take these quotients, we show that all of them are isomorphic and similar for the virtual twin case. Okay, so we have this isomorphism. So it means the following: since this group, since this quotient, now it means the quotient, since this quotient is crystallographic, so it means that also this quotient is crystallographic, also this quotient is crystallographic, and all of them have the same properties. So it's not really necessary to try in a separately way these other quotients. So we have the same information. The isomorphism for the case of virtual braid groups were pointed out to us by Paolo Bellingeri and John Waschke in personal communications. And so we don't need to consider separately these groups to study it, and also for the case of the other that are related to the virtual twin groups. Okay. Just a last comment about the Gauss virtual braid group. So it is not a crystallographic group. The reason is that the abelianization of the pure part has finite ordered elements. So this quotient is not a crystallographic group. This quotient means this one, okay? But doing the same, applying the same techniques we make for this quotient, if it is interesting, we may classify finite ordered elements, conjugacy classes of finite ordered elements, and realize virtually cyclic groups or Weber groups now, because it's not a crystallographic group, but we may realize some kind of objects that we did for the other quotients, the virtual braid group quotient, for example. Okay, I guess it is. So yeah, thank you so much for your attention.
Thank you. Do you have any questions or comment? If you have a question, please turn off your mute.
Hi, thank you for your talk. So I have a question. So we can't see these crystallographic groups for twin groups because you considered virtual twin groups, and then of course we have a sequence from Tn to Sn.
So sorry, Neha, what is the question?
I'm saying that can't we consider to study the crystallographic groups for twin groups because you consider different.
Okay, just for the twin case, yeah?
Yeah.
Not the virtual case. Okay, so the problem here, Nia, is the following. The pure, so the question is more or less the following. So consider you have not the virtual part, but the twin, just the twin short exact sequence. So you have here pure twin group.
Yeah.
They are also called planar braid groups.
Mm-hmm.
And the point is the following. This group is very difficult to understand in the following way. I need some presentation. And if I have the presentation, a nice presentation for this group, it will be possible for me or for us to start the analysis. But the point is, there exists in the literature some kind of presentation from Jacob Mostovoy. But the point is that this presentation of the pure twin group is very difficult for us to use it to do the computations. So this presentation is not completely friendly for our purposes.
Okay, got it. Thank you.
Mm-hmm. So I have the same question. PTN is complicated, but how about the modulo commutator subgroup? Is it a free abelian or finite torsion? There's a finite.
Well, Professor Kama, it is a good question. In fact, I don't know exactly. In fact, I don't know exactly how is the abelianization. So, well, there exists a presentation of this pure twin group, and we tried to understand it. In fact, the first step was trying to abelianize it, but was not completely friendly. So it's recursive, if I remember it well, and not completely easy to work.
So it's complicated.
Yeah,
Any
may
other
I add
questions?
something?
Yes, please.
Yeah, I think up to rank 5, it is known it is a right angle Artin group. So the quotient is free abelian in that case. But from 5 on, even for 6, I guess. But after that, we don't know.
Yeah, thank you, Mahenda. In fact, there are some works for few strings. One of them is from Jesus Gonzalez, studying some topology aspects But for the general case, in fact, we lost the control. But for few strings, it's more or less well behaved. Thank you, Mahendra.
You're welcome. Thank you. Thanks for the talk.
Thank you.
Okay, let's thank the speaker again.
Thank you so much.